Good day, everyone, and welcome to the U.S. Department of Energy's Fuel Cell Technologies Office webinar. We've got a great presentation this month from both Argonne National Laboratory and Pacific Northwest National Laboratory on the hydrogen carriers for bulk storage and transport of hydrogen. My name is Eric Parker. I provide program support within the Fuel Cell Technologies Office here at DOE, and I'm the organizer for today's meeting. We'll begin in just a minute, but first I have a few housekeeping items to tell you about. Today's webinar is being recorded, and the recording, along with the full slide deck, will be posted online. We'll be sure to let you know. Additionally, all attendees will be on mute throughout the webinar, so please submit your questions that you have about the presentation via the chat box that you see here in the WebEx interface. You can send them at any time, and we'll make sure they get addressed before the end of the webinar during the Q&A session at the end. And with that, I would like to introduce today's DOE webinar host, Ned Stetson, who is joining us at DOE headquarters. Hi, Ned. Take it away.
Thank you, Eric. Good afternoon or good morning, everyone, and thank you for attending this webinar on hydrogen carriers. This is an exciting time for the hydrogen community as more technologies are coming to market and demand is definitely growing. Today, there are 5,600 fuel cell electric vehicles on the road in the U.S. There are 35 hydrogen fuel retail stations open in California. There's now one open in Hawaii and about a dozen expected to open soon in the Northeast. In addition, there are over 23,000 hydrogen fuel cell forklifts in operation and hundreds of fuel cells being used for backup power, such as on cell phone towers. On top of that, there is growing interest in the potential hydrogen to benefit in helping improve the resiliency of the power grid, and this is especially important as the percentage of energy from intermittent resources such as wind and solar increases on the grid. Having the ability to store energy and or divert some of that excess energy to other high-value applications is becoming very important. And hydrogen has the potential to provide both energy storage and to be a pathway to connect energy sources with high-value end uses. So to this end, the DOE's Hydrogen Fuel Cell Technologies Office has launched the new H2 at Scale initiative. The H2 at Scale initiative is looking at how we can couple the various energy sources and high-value end-use applications through hydrogen. The initiative is organized around the areas of make, move, use, and store. The areas of use and store are critical in order to couple where and when hydrogen is made to where and when it's used, especially when these are being separated by both time and geography. Conventional methods to move and store hydrogen, namely as either compressed gas or cryogenic liquid, have limitations such as their low energy density, low energy efficiency, and high cost. Therefore, it's important that we identify and develop new and better ways to move and store hydrogen. And hydrogen carriers is one of the technology areas that we are interested in looking at that may provide benefits for both moving and storing hydrogen. So today's webinar will cover both a preliminary baseline analysis comparing some potential hydrogen carriers with conventional methods for moving and storing hydrogen, and some of the initial plans we have on hydrogen storage research through HIMARC. Just a couple of words on HIMARC. HIMARC is the Hydrogen Materials Advanced Research Consortium. It is a member of the Energy Materials Network, or EMN. The EMN was launched as a way to make the national laboratory capabilities more accessible to address the critical needs of industry and technology development. The HIMARC National Lab team is comprised of Sandia National Lab, National Energy Renewable Lab, Lawrence Livermore National Lab, Lawrence Berkeley National Lab, Pacific Northwest National Lab, the NIST Center for Neutron Research, and SLAC. This core National Lab team has two key roles. First is carry out foundational research to understand the phenomenon of hydrogen interacting with materials for both the uptake and release of hydrogen, and to provide world-class capabilities for the synthesis, characterization, and computation for material development. Individual projects are selected from industry and universities through, for example, funding opportunity investments to work with the HIMARC core team to help accelerate the project's progress. So this webinar today is being presented by Dr. Tom Autry of the Pacific Northwest National Lab and Dr. Rajesh Ahluwalia from Argonne National Lab. Tom is a chemist and has been a scientist at P&L for around 30 years and has worked extensively on hydrogen storage materials for at least the last 15 or so, including the lead role in the former Chemical Hydrogen Storage Center of Excellence. Rajesh has over 20 years of experience doing analysis on hydrogen for transportation and has led Argonne's efforts on hydrogen storage system analysis for well over a decade. So to have extensive background experience related to this topic, and I'm sure will provide a very informative webinar. So with that, I'll turn it over to you, Tom.
Thanks, Ned. Good morning, everybody. As Ned said, this is a pretty exciting time, looking at new concepts, looking beyond vehicles. And so I was asked to help organize this and got some help from our group here and the Highmark team. And so this outline will give you kind of a breakdown of what we hope to accomplish here today, give you some high-level definitions, concepts, definitions, objectives and goals. Argonne, then I'm going to pass it on to Rajesh and Dennis, and they're going to talk about some of the preliminary analysis that will get into more of the definitions of what we talk about, one-way carriers, round-trip carriers, and making carriers without hydrogen, give you some examples of that. Then Rajesh will pass it back to me, and then I'll kind of give you more specifics, as Ned mentioned, of what Highmark has plans to do, specific objectives to Highmark, some examples that we've pulled together, trying to identify gaps in knowledge. This is one of our big driving forces. Some of the tools, scientific tools that we're using, and using foundational research to kind of help enable rational design, and I hope I can get to kind of explain to you what I mean by that, summarize that, and then have an opportunity for questions and answers. Next slide. So as part of the H2 at scale, there's these new opportunities, as Ned mentioned, looking at intermittent sources of electricity as one of those. You know, how do we store this? Can we store it in chemical bonds and hydrogen? So bulk storage and transport of hydrogen is of critical importance, and that's a big part of H2 at scale. So these storage needs may range from daily to seasonal in duration, and transport distances may exceed hundreds of kilometers. So you may want to, store your electrons and chemical bonds at one place, and then you may want to transport that somewhere. And so trying to understand these issues and what materials will help you do that. So the Hydrogen Carriers research effort is seeking new concepts and materials that have potential to provide advantages over compressed and liquefied hydrogen storage and transport. And so I think Rajesh will give a nice kind of a benchmarking, if you will, of these other carriers, these hydrogen carriers that will compare to compressed hydrogen gas. Next slide. So some definitions. These might seem a little redundant, but hydrogen carriers are going to be hydrogen-rich materials, and so it's not necessarily the same requirements that will be for on board. So they may or may not be the same materials, but it could be liquid or solid phase. It's not just liquid phase, but solid phase materials could have some real specific applications. And they need to be liberated on demand, putting it through a reactor, getting the hydrogen off. So ideal carriers will have high densities at low pressures and near ambient temperatures. So the formation of the carrier and the release of the hydrogen should be as energy efficient as possible, and to minimize the energy penalty associated with the use of hydrogen to carry and transport that. So you can get a lot more hydrogen density in there, but you have to weigh in, well, how much, what's the economics of getting that hydrogen on and hydrogen off again. So it's not just how much, not just gravimetric and volumetric. As for vehicles, it's also the whole thing. How do you get hydrogen on? How do you get hydrogen off? Next slide. So just some real high-level, starting objectives for this. We want to investigate pathways that is going to optimize these hydrogen carriers to realize the most efficient, safe, and economical approaches to just generally transport hydrogen from a production facility to a city gate. And Rajesh will have a really good example of what we mean by that. And then we want to be able to facilitate geographically agnostic hydrogen storage. So the goals, to kind of the high-level goals here, we want to look at novel materials and new concepts in liquids and solids, and then kind of open this up to think about alternate approaches to prepare and release hydrogen from hydrogen carriers. Are there alternatives to just heating this up? So on the next slide. I think then, okay, so this is where I'm going to hand it over to Rajesh, and so he's going to give some examples of these hydrogen carrier pathways for 3 different options. So Rajesh, it's all yours now.
So for our initial study, we selected 3 liquid hydrogen carrier pathways, also abbreviated as LHC, to cover different classes of carriers. The examples here are liquid ammonia and liquid MCH toluene system, and these represent class of carriers that require, for example, a steam methane reforming plant for hydrogen production. On the other hand, liquid methanol represents a class of carriers that does not explicitly require a hydrogen production step. We also selected these looking at liquid ammonia and liquid liquid methanol, which are one-way carriers, whereas MCH toluene is a two-way carrier. One would think that ammonia and MCH are easier to produce using renewable hydrogen than methanol, which would also require a source of CO2. Our initial results are for a scenario in which LHC is produced centrally, transmitted via trucks to Citygate, located 150 miles away, where it is dehydrogenated. The gaseous hydrogen product is decomposed, purified to fuel cell quality hydrogen using PSA. The gas terminal here serves multiple functions, including bulk storage of hydrogen, buffer storage of hydrogen, and a facility to load and unload tube trailers for hydrogen distribution to refueling stations. So the table which is underneath that I don't have a control over, it shows, what's that? Yeah, so the previous one, which is underneath here, shows you some of the boundary conditions for producing and the processes for producing ammonia by Haber process, which is also decomposed catalytically at high temperatures. Methanol is also produced in our study by steam reforming to produce synthesis gas following commercial methods for synthesis of ammonia and purification. And MCH is produced by hydrogenating toluene over non-PGM catalyst and dehydrogenated at Citygate using supported catalyst. As a reference, we also include a gaseous hydrogen pathway in which hydrogen is produced by SMR, and the terminal now is at the production site since there is no Citygate to speak of. So in the next slide, we summarize. So if you go to the next slide, Eric, so it summarizes main assumptions, and I only want to touch on a few of them. So the first one is that the scenario that we've been looking at is for 50,000 kilogram hydrogen per day daily production. So this represents a entry level or a transition stage scenario. It would represent, for example, about 5 to 10% market penetration in a medium-sized city like San Diego or California. 50,000 kilogram hydrogen per day corresponds to 370 tons per day, and this is bolded here. Ammonia production, 350 tons per day. Methanol production, 890 tons per day MCH production. So as reference, commercial ammonia plants would have capacity of the order of 2,500 tons per day. So that's about 7 times as large. Some of the modern methanol plants that are being built would have capacity of 5,000 kilograms per day, so that's 15 times per large. The MCH toluene being demonstrated by Kyoto, so the pilot plant for that would have a fraction of the capacity that we list here. I also want to mention that we do have a 10-day geologic storage for plant outages, so that's part of the GH2 terminal, and that hydrogen is being distributed in 500-bar Type 4 tanks, which typically have a payload of 1,042 kilograms or so. So in the next slide, so whereas ammonia and methanol production and decomposition are mature technologies, MCH production and decomposition technologies are at pilot stage. So in the next couple of slides, I talk about some modeling results on hydrogenation of toluene and dehydrogenation of MCH. What our model shows, and this is consistent with what's happening at the pilot scale, is that one can get nearly complete conversion of toluene to MCH in a catalytic reactor operated at 240 degrees C and 10 atmosphere with a 4-to-1 hydrogen to toluene ratio. We do need a makeup of toluene, which is about 2.5%, and this is primarily due to the dehydrogenation losses that I'm going to talk about in the next slide. This is the dehydrogenation process is exothermic. There is potential for raising steam in larger capacity plants, but not something that we would consider at the scale of 50,000 kilograms per day hydrogen facility. So if you move on to the next slide, which is on dehydrogenation. So the hydrogenation step was conducted in a non-PGM catalyst. It is not considered a critical barrier. Dehydrogenation of MCH, however, is using a precious metal catalyst, in this case platinum on alumina, and there has been quite a bit of research looking at selectivity and durability of these types of catalysts. Our modeling study shows that in order to obtain higher than 95% conversion, we would need to keep the pressure down to about 2 atmosphere or so. And that would be a reactor operated at 350 degrees C. The PSA typically operates at 10 ATM, so we need a 4-stage compressor to raise the pressure of hydrogen from 2 ATM to 20 ATM. As I mentioned, there is about 2.5% loss of toluene and MCH in this system. We end up using 11% of the hydrogen that we produce during the dehydrogenation step. This tail gas is used in the natural gas to supplement the heating value of the natural gas in the hydrogen burner. In the next slide, we show you, or we summarize the results about levelized cost of hydrogen distributed to the stations. So our baseline case, the gaseous hydrogen, the levelized cost is $4.80. This includes producing hydrogen, includes transmission and distribution to the stations, but it does not include the station cost. So obviously the very limited scenario that we looked at, production and decomposition of LCH are extra steps. They incur about 33 to 47% incremental cost over the gas line, over the baseline of the GH2 scenario that we talked about. And the production costs line up as ammonia greater than methanol, greater than MCH. The decomposition cost goes the other way. That is the methanol, almost the same as MCH. So methanol is being dehydrogenated by a C-methane reforming step. This is a plain decomposition over MCH, is over a precious metal catalyst greater than ammonia. Transmission and distribution, we do save somewhat with MCH over the methanol that we, or rather, it's more expensive for the MCH rather than the methanol. I do want to mention that the scenario that we just described is for 50,000 kilograms per day. The DOE record is for very low production volumes, perhaps on the order of 1,000 kilograms per day, and the cost there is $13 to $16 per kilogram hydrogen dispensed at the station. Of course, we do not have the station cost included in our studies. All four scenarios that I just described, they all use geologic storage, which is not available at all sites. So the future studies will consider options taking advantage of liquid hydrogen carriers to circumvent the cost and non-availability of geologic storage at all sites. So in the next slide, some more results, and these are available in Argonne slides and were presented last year at the AMR. So this one, again, looking at the levelized costs broken down in terms of capital, operation and maintenance, fuel, and utilities. So 70% of the incremental cost in the ammonia and in the methanol plant is because of the added cost of the capital cost of making ammonia and methanol and decomposing it. For MCH, the capital cost is lower, and the balance is equally divided between O&M, fuel, and utilities. So in the next slide is energy efficiency. So not too surprisingly, the energy inefficiency because of the additional production and decomposition of LCH is about 50, can be up to 50%. And here we're making the assumption about that all the electricity that's consumed in these processes can be, we can come up with a single metric of fuel and electricity, assuming 33% efficiency, and the energy efficiency that we calculate, or the energy consumption, lines up as MCH, nearly the same as ammonia, at 2.52 kilowatt hour per kilogram hydrogen, per kilowatt hour of hydrogen heating value, greater than methanol, greater than the gaseous hydrogen step that we are looking at. So in the next slide, now we would like to look at scenarios in which the liquid carriers could be advantageous. So one way, and I hinted on that earlier, was to look at larger plants and take advantage of the economy of scale. If you look at these two figures, this gives you an idea about where the recent methanol and ammonia plants have been built in the United States. So you would see a concentration of these on the Gulf Coast. It takes advantage of the critical energy infrastructure that's available over there. It also takes advantage of the differential in energy prices, natural gas price in the Gulf Coast, for example, as low at $2.65 per million BTU versus California, which is at $6.80 per million BTU. So the scenario that we have looked at is a very large central production plant. So I hinted of that, talked about that typically these plants can be, for methanol, can be up to 5,000 tons per day. We look at even futuristic plants which might be at 10,000 tons per day, in which the syngas is being produced by ATR, and I will have something more to add to that. And then these are transmitted by railway, across to California. That's about 30,250 kilometers away, stored and then transmitted by trucks to the city gate. So what we are doing here is we are producing 10,000 tons per day, and we are siphoning off 350 kilograms of it because there is very limited demand right now. So the balance of the city gate looks exactly like what was in the reference scenario. So I have a couple of slides on talking about the economy of scale and how it affects. So the next slide is showing what type of the dependence of the methanol production plant technology on the scale of production at a low scale of 1,700 tons per day. The reference is one-step steam methane reforming. At the modern plants, almost invariably used SMR plus ATR for syngas production. So this is a two-step process at an even larger scale of 10,000 tons per day. Something that's talked about in the literature but has never been built is a one-step ATR-based syngas production step. So if you go to the next slide, so you can look at the capital cost, how that depends. So that's in $1 million per ton per day of methanol, how that varies with the plant capacity. So going from 350 tons per day, which was the case that we were looking at, if we actually could go to 10,000 per day plant, why there is almost a factor of 2 decrease in the capital cost. So at the right, you see this was our reference case, very low methanol production capacity, and this is the intermediate case. 10,000 tons per day is what I want to present a few results. I just wanted to mention that about 50% of the total capital cost, regardless of the technology that we were using is in the reformer, air separation unit, and or CO2 removal. So that accounts for about 50%. I also wanted to mention, and that was an advantage that was discussed before, that the storage cost represents a small fraction of the total capital cost. So if you put all these information together in the next slide, so now we can look at the levelized cost of hydrogen for the scenario of a very large centralized production of methanol in which a small fraction has been siphoned off for production of fuel cell quality hydrogen. This is a result that I presented earlier at the small scale where the cost was $6.70, and now we see that with the new scenario, the levelized cost is very competitive with the baseline GH2 scenario. So where did the savings come from? The saving came from, 50% of the saving came from the economy of scale. Other 50% came from the lower cost of the feedstock. So in the next slide, so here's a summary of where we are going. The first part is to calibrate our initial results. So we've been talking to the various experts, looking at the field data for ammonia and methanol plants of different capacities and seeing and refining our estimates. We are also talking to OEMs, looking at if we can verify, validate, and calibrate our results for MCH production and dehydrogenation. We will continue to look at scenarios that favor hydrogen carriers. We are looking at different demand and supply scenarios, for example, with byproduct hydrogen, where the LHT step can be particularly advantageous. We also want to look at renewable hydrogen, and I had a couple of sentences about why ammonia and MCH may couple very well with renewable hydrogen production. And the last one is to do reverse engineering and coordinate with Highmark. And on that note, I am going to hand the control back to Tom.
Thanks, Rajesh. Eric, then let's move to the next slide, and that number 5 will start to become apparent. So what I wanted to do was give you some more specific objectives of Highmark. I mean, there's the objectives of the hydrogen carriers at a higher level. Then Highmark really is going to continue their role as, trying to leverage our capability and expertise, for accelerating progress in carriers. And so we're looking to the community for development of new materials and, and ideas, and we're available to help with accelerating progress and doing research in that area. But kind of beyond that, when we started to think about how we would define our roles, we want to, look at what are the important properties of hydrogen storage materials beyond, onboard vehicular. So determining advantages and limitations for materials and approaches to carriers for transport, which the material could be different for transport than for long-term storage or even for short-term storage. So, all these different materials, what would be the advantages and disadvantages for all different applications. We're interested in looking and trying to understand novel approaches to release or absorb hydrogen onto carriers, and I'll try and give some examples of that to follow. We're characterizing novel approaches to preparing carriers that do not require this discrete step of making gaseous hydrogen. Can you take electrons and protons from water and store those in carriers? Is one example. Rajesh gave example of methane to methanol formation. Both of those, you don't need to have make hydrogen and store that in a separate step and then add that. Comparing approaches that can be used to prevent phase changes. I'll try and give some examples of that. It seems as though hydrogen-rich materials are soluble or stay liquid, and then as they start to lose hydrogen, then they could start to solidify. And so how do we prevent that? And then catalysis is going to be important in trying to understand, all the different things you need to consider in catalysis, the stability, the cost, the rates. The rates are going to depend, again, on how much hydrogen you need at any given time. And so all these different applications could have different needs that are more important for one application or another. And heterolytic versus homolytic activation of hydrogen for putting hydrogen on or taking hydrogen off. And then validating concepts for rational design. And I hope I can kind of explain what I mean by that. Next slide, Eric. So I want to move into some examples. These are by no means the only examples or primary examples. I'm hoping to provide these as things that could seed new ideas. We do a lot of electrocatalysis at our laboratory, and so I have some colleagues that I like to listen to and learn from. And so can we do electrocatalysis? And, just some simple examples of CO2 to formic acid or to formate or even on to methanol. What kind of could you do electrocatalysis to do that? And are there advantages of electrocatalysis over thermal catalysis? Taking phenol to cyclohexanol, could you do that electrochemically without having to make hydrogen in a discrete step? And so then it becomes, can you run that backwards without having to generate hydrogen, or can you use these, transport this around, release hydrogen, and run this through some sort of fuel cell? So lots of possibilities. The next slide. Some other examples that I'm kind of fascinated by personally are aqueous mixtures of organics. So here's an example I give of an alcohol where half the hydrogen comes from the alcohol and the other half comes from water. So if we want to store something in a smaller amount of volume and transport it around, could you transport the water? Transport the alcohol or store the alcohol, and then later on, wherever you need to get the hydrogen off, you then double your volume, but you get part of your hydrogen from water. And so, this would be where water is readily available, and there's cost to that. Water's not free. But, this is interesting chemistry, the reaction to make the acid, that's uphill, and so that's endothermic. But are there ways that you could tune the thermodynamics of the acid by stabilizing it as a base, with a base as a salt? And so the free energy for the reaction is going to be proportional to the pKb of the acid and the base pair that you choose. And so you could, this is kind of potentially an example of a rational approach to looking at designing some material, so understanding how you can tune the thermodynamics. On the next slide. This is comes back to one of the things we've started to talk with Rajesh and Dennis about, is this formate bicarbonate cycle. I find this, this is like one of the perfect hydrogen storage from a thermodynamic point of view. You can take formate and dissolve it in water. If you throw in some catalyst and you wait long enough, you make bicarbonate and hydrogen. And so this is an example of some NMR studies we just recently did with some colleagues and coworkers, where we just followed this reaction at 20 degrees. And so it starts at the bottom where we start with formate, and then having a catalyst in there, it releases hydrogen and makes this bicarbonate, and the equilibrium constant is about 1 for this. So this reaction is readily reversible. And so there are lots of things to ask good questions about this, about, solubility, again, of the product versus the starting material. What kind of catalyst do you want to use? What do you do with the bicarbonate once it's formed? Do you get credit for taking CO2 out of the atmosphere, or do you can recycle this? And so that could all those sorts of questions could depend specifically on the application you want. Formate is pretty benign compound. We've talked to other people working in the field, and they pointed out to me that it's being looked at as a road de-icer, and so there, it's kind of a nice non-toxic, relatively environmentally safe material. So if you could store hydrogen in quotes on formate as a solid, and add water later when you needed to get the hydrogen off. So half the hydrogen again comes from the carbon and half comes from water. You can minimize your volume density. And so is there advantages to that, and when are there advantages to that? Next slide, please. Another thing that I've been really fascinated by is what I've been calling chemical compression, and chemical compression may have different meanings in different places, but what I'm talking about here is that if you have some compound like ammonia borane, it decomposes and you can never regenerate it because the pressures you have to go to are so high that you can generate high pressure of hydrogen. But formic acid is really interesting because delta G is negative and delta H is positive. So this is better than ammonia borane. And that the reaction isn't going to have thermal runaway. So you can, it's entropy controlled. As it decomposes, you make hydrogen and CO2, and you can generate pretty high pressures. And so how do you compare apples and oranges to figure out, is there some way we can minimize physical compression? Can we use like formic acid decomposition to do the first stage of compression? And so when would that be important, and how valuable is that? And so then there are lots of questions they ask and try and understand, how do you do separations then of CO2 and hydrogen when you get to these high pressures? You need to control the selectivity, so you get dehydrogenation instead of dehydration. And then, what are the best approaches to make formic acid? Because, it is going backwards and you have to go uphill. How do you form that, and what's the cost of that? So how do you compare the cost of making formic acid to the cost of a physical compressor? Is a really oversimplified way, but these are the sorts of concepts we're trying to understand. On the next slide. So this is really too wordy, I guess, but what the title is really probably, what I really want to get across here is that Highmark is really trying to address, gaps in knowledge, right? And so I touched upon some of this with the chemical compression. What kind of reactors do you need to design for these liquid reactions? It depends on the rates at which you need hydrogen. Again, if you need 2 grams of hydrogen per second, then it's going to be really difficult if you have to worry about a 3-phase gas, solid, liquid interaction. And so is there, if you don't need the hydrogen at those sorts of rates with this, looking at these gas, liquid, solid reactions, when do you have to worry about that? When do you not have to worry about that? And then some of them are just really more foundational in nature, about designing proper catalysts that are more economical, that have long stability. And so with the expertise in Highmark and the molecular foundry and all the expertise in making MOF and materials and catalysis, hopefully we can address some foundational questions there. And then just kind of on almost the other end of things, for characterization, liquid phase PCT, so pressure composition isotherms are used to get very valuable information for solid materials and metal hydrides. And so, if we develop PCT approaches for looking at liquids, and what would even a PCT curve for a liquid look like is if you have multiple hydrogens coming off of methyl cyclohexane to make toluene. Are there, what are if you can get the thermodynamic data, that would be really valuable, but it's going to be tricky to do because it's a liquid. You have to worry about the vapor pressures of these things, and again, the expertise of the people at NREL are going to be able to answer whether or not this is feasible. What can we learn from this, and are there better ways to do this? And then just kind of at the end, I think I'm going to touch upon this about fuel blends. Again, this comes to this low vapor pressure, and so are there ways you can make liquids by blending materials? And so I'll try. I think I'll have an example of that coming up. Eric, the next slide, please. And so I'm moving, I guess, here into some research tools. And so the PCT is one of them that we're looking into and talking to NREL about. But my coworkers here have done some really fascinating work, really nice, elegant ways to look at liquid phase transformations by NMR spectroscopy. And so PNL really, tries to bring in NMR capability into the Highmark team to help out everybody in Highmark, as well as people that are being funded in individual projects by DOE. And so this just gives kind of this nice example of this peak NMR tube, where it's been pressure tested up to 1,000 bar. The temperature range is in kind of the area you'd want for a material. So, if you want to do more stuff at lower temperatures, we'd have to think about ways to do that, or higher temperatures. But this gives an example of measuring in equilibrium as a function of pressure. We can do this as a function of temperature. So, again, a way to get some thermodynamic data on, in this case, these liquid carriers. On the next slide. This is another example of what we've been trying to develop, ways to look at both thermodynamics and kinetics, and it shows some calorimetry. We are looking at some liquid carriers and trying to benchmark some of the nice calculations that were done by Air Products and other people, where we can get thermodynamic and kinetic information here. And so you can integrate the area under that curve and get your thermodynamic data, and then you look at the time dependence of that, and you can get kinetic data. So we've been looking at different catalysts, and so we have a direct way of kind of monitoring efficiencies of catalysts as far as looking at rates of reactions. Next slide. So here I want to give a couple examples of what I consider rational design. And so this is, where, we're trying to come up with ways to keep things from doing phase separation. And so when we had the opportunity to work with our coworkers at US Borax, they had pointed out to us that there's these solubility tables, and if you vary the ratio of the metal to the boron, you can change the solubility. And so one of the problems with the sodium borohydride was the stability of the product. The borate is less soluble than the starting material, so you're limited by that. And so if you can come up with a material that had a Q, which is this ratio of metal to boron of 0.3, you get, twice the solubility of the products. And so when you look at that, you say, well, that could probably be, sodium, like a tetraborane or a triborane. And so the triborane, was a lot of nice work done by a number of groups, and that's water stable and water soluble, and that has an opportunity to give more hydrogen than the borate. But the challenge with this was one way, and so making these materials was the challenge. But this is kind of an example of rational design, some way to predict what you can do to help a class of materials. On the next slide. I think here's another example that I really liked from the literature, where you could predict the thermodynamics of hydrogen addition to an arene, a cyclic compound, by knowing what its Hammett parameter is. And so here it shows different classes of materials, of phenol, indoles, piperidines. They all have a slightly different slope, and those are the Hammett parameters down there on the x-axis. And so if you know what the Hammett parameter is, you can predict what the enthalpy for hydrogen addition is. And so what I would like to know is what determines the slope of these materials. And, then could you use computational approaches to look at the two extremes of that and get the slope of the line and then make some predictions about new families of compounds for the enthalpy of hydrogenation and trying to understand how to lower that. So I think the next slide is getting close to the summary here. Really, we this kind of throws a bunch of things up there, kind of summarizing things where we really want to help DOE and our co-workers understand, how these alternate concepts. Making hydrogen carriers without making hydrogen. One approach is electrochemical I touched on. Is using water as a reactant and storing it, the compounds separately, a good way to reduce volume of these things. How useful and valuable and when is chemical compression going to be helpful. But you have to worry about the selectivity, integrating separation technologies, preserving the liquid phase. When we look at the formate and bicarbonate, bicarbonate is at least half the solubility of formate. What can you do about those sorts of things? Are there ways that you could integrate electrochemical and thermal processes to enhance some way to get hydrogen off and on or cycling? Bio-inspired processes. Eutectic systems, this is something that we're interested in. Can you take two solids, bring them together, make a low melting liquid, and then use that, and then preserve a liquid throughout. And then solids are going to be important as well, and moths and coughs, and when would those be valuable in what sorts of circumstances? And another thing that we've kind of been curious about from a foundational point of view is heterolytic absorption of hydrogen on materials versus a homolytic scission, and then dynamic materials. And so with that, I kind of that's the summary of what we've got. And so I think now it's on time to try and answer some questions.
Yeah, thanks, Tom and Rajesh. Reminder for everyone, if they haven't already, submit their questions via the chat box, and I'll turn it over to Ned to address some of the questions we've gotten already.
All right, thank you, Eric. So we have several questions submitted, and actually I will assign the first question to myself. The question is, DOE going to develop key technical targets for hydrogen carriers, e.g. energy density, conversion efficiency, et cetera, for different applications? And the answer is yes, we're in that process. One of the reasons we initially asked Argonne to start the baseline study is so we can actually start understanding how do carriers, which people have researched to this point in time, how do they compare with the more conventional ways of moving and storing hydrogen? So we can actually start seeing where are the needs for materials and where do we need to improve materials. At the same time, we're also looking at all of various in-use applications being considered under H2O scale to identify the needs for those applications. So again, we can start identifying what are the key importance, what key parameters are important for the movement and store of hydrogen, and how can carriers address that. So we are in that process. We will be at some point issuing some technical targets, but we don't have them ready at this point in time. So the main comparison today is what are the advantages of any carrier that's being developed with respect to either compressed or liquid hydrogen. So moving to our second question. So Rajesh, since you kind of went before Tom, I will give you next two. So first, it starts off with a comment. Great study. I have not heard of anyone considering gaseous hydrogen for bulk storage, only liquid hydrogen. Will liquid hydrogen be analyzed and compared as well? That's for you, Rajesh.
Yeah. So I think we're not quite done with gaseous hydrogen because, as you know, the bulk storage of gaseous hydrogen, when we talked about 10 days worth, that's 500,000 kilograms. is a big challenge. We don't want to rely on geologic ways because they are not always available. So there is work to do just with the gaseous hydrogen, but liquid hydrogen is definitely another reference in addition to the gaseous hydrogen. The reason we didn't look at it so much was because other institutions, including Argonne, AMGAD, and Sandia, they have looked at the liquid hydrogen, but yes, that would be a good comparison also.
Okay, thank you. And the second question for you, Rajesh. What was the criteria that got methylcyclohexane toluene selected over the historically used decylene, tetraline, naphthalene, et cetera?
Yeah, I think they're all very good options. I mean, we didn't quite touch on Hydrogenious, what they are doing. We regard them as competitors. They all have advantages. We selected MCH because this was not meant to be an exhaustive study of looking at all the options, but where we could clearly see some advantages or some uniqueness. So we looked at MCH, toluene pair, and others are competitive as well. And the reason we looked at it is because a pilot plant is being built in Japan by Kyoto. So it was a good reference for us to look at since we can also talk to those people. And I already noted how this would couple very well. Yes, there are definitely other pairs that may be equally good and some may be equally better. Or some may be even better, and I think we may look at those options as well.
Okay, thank you. And Tom, I'll give you a couple now. So one question we have is, can the bicarbonate react with calcium hydroxide to release additional hydrogen? Calcium carbonate could be a marketable chemical, or could calcium carbonate be a marketable chemical?
No, good question. I think, I mean, we've been talking about this when you're looking at these scales of 50,000 kilograms per day for storage. Is if you make 50,000 kilograms of something else, is there a market for that? And so there might be some, smaller amounts that you could use, but I don't have an answer for that. I think all things should be considered. Can you do something with these byproducts? It'd be a good question.
Okay, thank you. And Tom, I'll let you take the first stab at this, and then I may chip in as well. So the question is, some of the paths shown emit CO2 at the point of use. Is that a consideration?
That one I don't know if I can touch. I'm going to punt on that one because I'm just not going to say anything that's going to get me in trouble, I guess. I'll let you handle that one.
I thought that was going to be the case, Tom. So yes, CO2 emission is a concern. However, if it's a technology that consumes CO2 on the formation of the carrier, and then that CO2 is released again, so the net emission of CO2 is near zero, then that is definitely something of consideration. One of the issues with carriers is that even though we may have a perfectly reversible reaction, we are, temporarily and spatially separating the generation or the uptake of hydrogen generation of that carrier versus where hydrogen gets released. So in that case, where CO2 would be released again. So our preference would be carriers and pathways that have at least near zero emission of CO2. Okay, so I'll actually take the next question again. How does DOE design its targets? How are the targets used? Thank you. So thank you for this question. And we take a number of different factors into consideration when we establish targets. So as I mentioned, we have Argonne carrying out this baseline study now. Highmark is starting some foundation research, which will also provide us some input. But we will be carrying out various methods such as workshops on carriers, where we get stakeholders, and hopefully a broad range of stakeholders, from people who would be producing hydrogen and generating carriers, the people who would be transporting and using carriers, and people at the end use, get feedback from these stakeholders. We could also do surveys and request for information to get information, and then we pull that information together, and then we go back and again, taking all this information, we then try to determine targets based on the input from the end use and the stakeholders. So let's see.
Ned, can I just add to that? You mentioned the workshop, and then I forgot to mention that we will be doing a workshop on hydrogen carriers the week of February 11th. It'll probably be 1.5 days. It might be the 12th and 13th. I'm working with Tom Jeanette at NREL to organize that. We have the rooms for, I think, the 11th, 12th, and 13th, or at least the 12th and 13th, so people travel in on Monday. And so we'll address some of those, getting stakeholders in and trying to get feedback from a larger group on answering those questions.
Okay. I think we have time for one more question, and we do have one here. Tom, this is for you. Have you considered the autothermal cycle described by Air Products, where reversal partial oxidation of the carrier delivers the heat of reaction for the dehydrogenation?
We haven't. We looked at that a few years ago. I mean, that's an example of a creative approach, an alternative approach to doing these things. And so, at the time, we were interested in coupling exothermic and endothermic reactions together and using an exothermic reaction for releasing from the BCN compounds, the cyclic BCN compounds. One of those steps is exothermic and the others are endothermic. And so Kristen Brooks helped with some of that analysis, and that's a great example of alternative concepts that need to be looked at to try and couple of these things. So I've looked at that, I know about that, and that is a good example of an alternate approach to things. And there's no right answers or wrong answers right now. So.
All right, thank you, Tom. Thank you, Rajesh. I think we're getting close to the end of the hour here. So I do want to thank all of you for listening to the webinar, and I will turn over to Eric in just a minute. But I do want to repeat or emphasize what Tom mentioned, is that there is a workshop being planned by the Highmark team. This will actually be very valuable input into the DOE consideration for targets. We are working on the H2S scale, so you'll be hearing and seeing a lot more about H2S scale going forward into the future. And again, all this is being integrated into the H2S scale framework. So with that, I would like to thank all of you from the DOE side for attending and listening to the webinar. And if you have any questions, please feel free to submit them to the website, or you can send them directly to myself. So with that, Eric, I'll turn it back to you.
Yeah, thank you, Ned, and thank you, Rajesh and Tom, for a thoughtful and informative presentation. That does conclude our webinar for today. If we didn't get to your question or you think of one later, please feel free to email Ned or the presenters, like you mentioned. And also be on the lookout for a recording and the presentation files to be posted online in the near future. And I encourage everyone to sign up for the monthly newsletter, which includes information on future webinars and workshops like those mentioned. With that, I'd like to wish everyone a great rest of their week, and goodbye.
No, you have to press it.